Let's talk about beta-dicarbonyl compounds. So the beta just means 2 carbons away. So beta-dicarbonyls have carbonyl compounds that are 2 carbons away from each other. So we talked about acetone as having a pK of around 20, and I said that that means that just OH minus, hydroxide or methoxide or ethoxide, whatever, all of those aren't going to cut it. They're not basic enough. However, the hydrogens between the carbonyls are quite a bit more acidic than the hydrogens on the outsides here. So the outsides is basically the same as acetone, pK about 20. But here in this diketone, that's a pK of around 9. And for this beta-keto ester, ketone on one side, ester on the other side, here those are pK about 11. So both of these are more acidic than water on the middle carbon. So that difference in acidity gives me some really useful selectivity. So if I give this a weak base like NaOH, I can be sure that I'm going to deprotonate between the carbonyls and not on the outside. So this is going to be my enolate. That's what's going to react with my methyl iodide. In this case, I can just mix my NaOH and methyl iodide all in the same pot because the NaOH will fully deprotonate my carbonyl compound. And the enolate, again, fully formed, will do the SN2 reaction I want, and I'll get the ketone that I want. Pretty cool. And the same thing is true for the ester, right? So I'll always be able to deprotonate in the middle. Here I've got a beta-keto ester. What happens if I give it excess base and excess electrophile? What's excess? I don't know, 2 equivalents, 5 equivalents, 10 equivalents, some big number, right? So again, no matter how much base I have, the base strength is only going to let it react in the middle of this thing with these more acidic protons. So just as before, we deprotonate between the 2 carbonyls, we get a nucleophilic carbon, we do an SN2 reaction, we make a new carbon-carbon bond. Cool. So now we've got the product in the pot, but the product is around lots more base, and there's still an acidic proton there. So we'll actually see another reaction. My excess base takes my still very acidic proton here. I get this new enolate, which then attacks my methyl iodide, and here I have now added 2 equivalents of my electrophile to this carbonyl compound. Again, the cool thing about this is the chemoselectivity. Because this is a weak base, I can count on it to only react in the middle of the molecule and not to go after the things on the end. And not to go after the things on the end. Notice that here I'm using ethoxide because I have an ethyl ester, right? If I used methoxide or propoxide or something like that, I would be a little worried about transesterification, switching it back and forth. But here, I don't need to worry about that. However, a strong base like LDA is able to react at both the middle and the outside of this, right? So the pKa for this is about 11, the pKa for these are about 20, but LDA, the conjugate acids, the pKa is still in the mid-30s. So this is a strong enough base to give me the dienolate here, right? So now if this reacts with one equivalent of iodomethane, it's going to react at the more reactive enolate, which is clearly this one, right? It's kind of a last hired, first fired type of situation, right? So this is much higher in energy because it's not as stable as this one. So we're going to react here first. Notice that the product of that reaction is still an enolate, right? We still have this stabilized enolate here. Now this enolate we can then react with either another equivalent of methyl iodide or some other electrophile to make a new bond here. Here that enolate intermediate, let's say we give it some propyl iodide midway through the reaction. Now that's going to make a new carbon-carbon bond and I'll get this dialkylated compound. So again, a strong base like LDA, I can get the dienolate and then react with the most reactive and then the less reactive enolate in sequence. So beta-dicarbonyl compounds are pretty cool for a couple of reasons. I can react them really regioselectively. I can either put two alkyl groups in the middle of it, or I can put one in the middle and one on the outside. I've got a lot of control over that. So that's pretty cool. But maybe the coolest thing I can do is this sequence here. So here, let's say I've got some beta-keto ester. I'm going to hydrolyze the ester. So I'm going to treat it with aqueous base and get this O-. And then after that, I'm going to re-acidify. So first base, then acid. And that just hydrolyzes my ester, and I have this beta-keto acid. So this is kind of a unique thing. If I heat this, magic happens. So here I just drew the beta-keto acid twisted around. But when it can twist like this, it forms a six-membered transition state where electrons are going to rearrange. When they rearrange, I end up losing carbon dioxide, so I lose CO2. And over here, my electrons form a new bond between oxygen and hydrogen here, a new double bond. That's just an enol. And as soon as I form an enol, remember that keto-enol isomerization is fast. And so as soon as that enol is formed, it's going to go right to the ketone. So in essentially two steps, basifying and then heating it in acid, I go from this beta-keto ester to this ketone, right? So I'm actually losing this whole piece. I lose this whole ester piece and go directly to there, right? This is called decarboxylation because I'm losing a carboxyl group. Your body does this a lot. So decarboxylation reactions are really, really important biochemically. But this is how we do it synthetically. Why is decarboxylation useful? Well, for one thing, it's important for us to understand biosynthesis, so how our body's enzymes work and make the chemicals that keep us alive. And decarboxylation is a big part of that. But there are practical uses to it too. For instance, let's say I wanted to deprotonate this thing with LDA. On what side is this going to deprotonate? On this side or on that side? We're going to end up with both enolates, which is not going to help us get a high yield of one product the way we want. Right? So here we needed to use a really, really strong base, and we have no regioselectivity. Let's come at this problem a different way. Here, I've changed my starting material. Now I have a beta-dicarbonyl compound as my starting material. So now I don't need to use this really strong base. I can get away with a much weaker and easier to use base like sodium ethoxide here. And I can just chuck it in with my electrophile methyl iodide. Here I've added my methyl group regioselectively, which is to say on the right side that I want, and completely selectively. I don't have to worry about reacting at the other side like over here at all. And then once I have this, I just cook in base and then cook in aqueous acid, get the beta-keto acid, do the decarboxylation reaction. So again, just cook in base and acid, heat it up. You lose CO2 as well as ethanol in this case. And you end up with this alkylated ketone, which is what you wanted. And you end up with it in high yields, gentle conditions, and regioselectively. No addition on this side of the carbonyl. So beta-dicarbonyl compounds, much, much easier to alkylate. And if you're talking about an ester, I can make that ester go away by decarboxylation reaction. And that's useful too for selectivity issues.